Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video on math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside as we jump into section 5.6 in the Big Ideas Math Integrated Math 1 textbook on graphing linear inequalities in two variables. Now, we did an entire chapter based on inequalities, but it was with a single variable, generally x, or maybe they use different letters, I don't know. We would graph it on a number line, left and right, that's a single dimension, and to the left is less than, to the right is greater than, things like that, closed circle, open circle, and boundary points. You get the picture. That was one variable, now we're in two variables. Now, we are in a chapter on systems of equations. The next section, I'm going to let you know, has systems of linear inequalities, but first we got to understand how to just graph linear inequalities in two variables, like we do with x, y, a line with a slope and y-intercept, but there's more to it. There's this shading aspect. We're going to talk about that. How does the boundary line work? What kinds of points should we test out? That's what this section's all about. We have 45 questions in total we're going to do. I'm going to start with the lecture portion. If you'd like to follow along with any of this besides the video itself, find the PDF down below in the description section, as well as PDF stuff of graph paper. We are going to have to be doing a bunch of graphs, I'm sure, because that's really how the solutions work on these things. And also timestamps. Timestamps, all the problem sets and stuff are down below. Without further ado, I'm going to go ahead and get started lecturing. We are going to check solutions of linear inequalities. Basically, see what it means to make a test, plug in x, y values, see what works, what doesn't. Graph linear inequalities in two variables. That's what the whole section's all about, of course. And use linear inequalities to solve real-life problems, the word problems, as always. Lecture does us like that. I don't know what half planes mean. Well, now I think I do, but I'm going to say the word region most often. I'm going to say a shaded region, not a half plane, but all these other ones will pop up as they do. A linear inequality in two variables, x and y, can be written as any of these. They look like standard form, right? Ax plus by equals c, you know, like that. Only now we have different kinds of inequalities. Less than c, less than or equal to c. Greater than c, greater than or equal to c. You could also rewrite them in slope-intercept form if you so choose, and we'll talk about that, or the book will talk about that, I'm sure, at some point. A, B, and C are real numbers, and a solution is an ordered pair that makes the inequality true. Remember, in standard form things, we try and see when the left side equals the right side. But now when we have inequalities, we want to see when the left side is less than the right side, or when it's greater than or equal to the right side, and things like that. What makes it true? That's where our solutions will appear. Now, there's an infinite number of solutions. It's not just the line, and sometimes it's not the line itself, but what's above it or what's below it is something we're going to be talking a whole lot about. All right, checking solutions. Tell whether the ordered pair is a solution of the inequality. No graphing yet, just a substitution. We have this inequality set up right here, and we have this ordered pair. -1 for x, 9 for y. So let's substitute them. 2 times -1 plus 9 is 7. Is 7 less than -3? No. So -1, 9 is not a solution to it. Now, it's very specific for that x and y, it's not a solution. That's not to say that x is -1 can't make a solution given the right y value, and same with the 9 for y, you can't do it with a certain x value, but that specific one, no bueno. Let me sinking a little low there. Part B, x minus 3y is greater than or equal to 8. Let's plug in 2 for x, -2 for y. You get 8 on this side and 8 on that side. Well, as long as it's greater than, nope, as long as it's equal to, yup. So as long as it's equal to, it looks like it works out. So this is a solution. If this said greater than only, and remember, they gave us the inequality, but if this said greater than only, it wouldn't be true. But because it's also equal to, it does work out. So those are two examples. They have a couple others we can plug in here. My favorite one to always test when it comes to values will be 0, 0, especially how fast it goes. I just want to make mention of that. 0 minus 0 is 0. Is 0 greater than 5? No, it's not equal to 5 either. So that's going to be a nice easy test that we do, and one we're going to do quite often when we do graphs. All right, speaking of which, the graph of a linear inequality shows all the solutions of the inequality in a coordinate plane. Now, they have a couple things here. They have the line that you would generally write for your equations, like y equals 2x right here. There's that line. But this is now something we're going to call a boundary line. Now, I don't know if you recall, but in Chapter 2 with inequalities, I referred to the point on a number line as a boundary point, like an open circle kind of thing or closed circle. I called it a boundary point. I don't recall the book ever actually saying that phrase, but I called it a boundary point. This is a boundary line. Just like a boundary point, it's the threshold between what are solutions and what are not solutions. Same is true for this boundary line. It separates what are solutions from what are not solutions. Now, they refer to this as a half plane being half of graph that's shaded in half that's not, I'm just going to call it a region. I'll call it a shaded region, unshaded region. There's a region above, a region below, things like that. I'm going to state those. So the boundary line divides the regions for which there are solutions and are not solutions. Remember the number line again. On a number line, what else would we do? We would also draw arrows on the thing. So if I had here's 0, here's 3, and here's greater than 3, I would draw an arrow that way to say here are all the points that are solutions for x's that are greater than 3, for example. Well, we're not going to, just like we don't plot a bunch of points right here, we draw a line. Here we're not going to plot a bunch of points. We are going to shade our region. So we are literally going to take our pencil or whatever it is that you have, probably a pencil. I recommend a pencil. And shade that region. Everything that's on this side of the line, on that half plane, will represent true statements for the specific inequality. Which one are we talking about, by the way? It's this one. Y is less than 2x. So anything that's less than 2x, y's that are less than 2x goes right here. And that's the solution set. Now, we haven't gotten to why we shaded on that region versus the other. I also haven't even brought up the fact that this line, it's not solid. It's a dotted line. Let's see. Do they call it dashed? Okay, dashed. I'll try and say that phrase. It's a dashed line. It's a dashed line. It's broken. It's dotted. It's dashed. What makes that so? Well, we're going to get into all that, I'm sure, on the very next page. But those are things to look into. This is what our graphs are going to look like. So graphing it. We're going to graph the boundary line first. So imagine it said y equals, right? Y equals this thing. Or in standard form that it says something. You graph the line as you know how to. Now the line may be dashed or it may be solid depending on whether it's equal to or not. We use a dashed line for less than or greater than. We use a solid line for less than or equal to or greater than or equal to. It's like the equivalent to a boundary point's closed circle versus open circle. A dashed line represents points on the line aren't solutions. Just like the open circle, a point on the open circle would not be a solution. Closed circle is like the equal to, something that we're very familiar with doing, obviously. We draw solid lines all the time. There's never a time you did a dashed line unless you've graphed inequalities before in this way. Then they say test a point that's not on the boundary line to determine. My recommendation is 0, 0. Now, that being said, that y is less than 2x. 0, 0 is on the boundary line. So I would try something else like 0, 1 or 1, 0. Try something small. 0, 0 is great because the x's and y's straight up cancel out. Now, eventually, I'm going to talk about how we can determine whether to shade above or below based on what form we're in. If we're in slope-intercept form, I'll talk more about that. We'll get into that if the book doesn't. But otherwise, for now, they talk about testing a point. I'm going to recommend 0, 0. If 0, 0 is a solution, the point that I test, I'm going to shade on that side. If 0, 0 is a solution, then everything on that side with 0, 0 should be a solution. If 0, 0 is not a solution, then anything not on that side should be a solution. And when I mean sides of the boundary line. Which region, again, they say half plane, I say region. Which region it's on. So we're going to shade one side or the other based on whether it is a solution or not. And that's going to be our test. That sounds a lot like what we did with the number line things, just two-dimensional now. So they say graph y is less than or equal to 2 in a coordinate plane. Now y equals 2 is what we're going to draw first. It's that horizontal line across the y-intercept of 2, slope of 0 like that. Notice since it's now less than or equal to, because it's still equal to, we will use a solid line. So graph y equals 2, just as you normally would. How do we know whether to shade above or below this line? Well, we can test a point. Such as, notice how they tested 0, 0. That's the wise one to test, and I think they're going to test it as long as it's not on your line. So you test 0, 0. Obviously, 0 for x doesn't matter, and that's kind of part of the point. It doesn't matter what 0 is, as long as y is less than or equal to 2, right? But you plug in 0 for y. Is 0 less than 2? Yes, it is. That's a true statement. Therefore, anything on the side with 0, 0 will also be a true statement. You can try and plug in 3, 1 or 4, -7. It would all work. And anything above it, like -1, 6, that would not work. So anything below would also work, so we shade that whole region. Anything down here is a point. So we shade that half plane, that region. Let's try this one with two variables this time. -x plus 2y is greater than 2. Now, they give this. They say you can either graph this or this. Why do they show both? Well, one of them is graphing out of standard form. What I would say is x-intercept of -2. Boom, right there. A y-intercept of 1, if you know what I'm talking about, I'm dividing by 2 here. Y-intercept of 1, boom, like that, and draw the line. Or rewrite it in slope-intercept form. This is kind of what they did here. Now, slope-intercept form does have its merit. It does have something beneficial to it, which I will be getting into in some problems, especially if they, well, it depends on if they already present them that way or if they ask us to put them that way. But you can graph one or the other, whichever you're comfortable with, okay? Now, given that this thing originally said greater than, you really want to go with the original. But given what this thing said beforehand, it didn't say equal to as well, therefore we will have a dashed line. Now, why do we shade on this side? Well, when you try a point like 0, 0, and you find out that it doesn't make a true statement, you can see when you plug in 0 here, you just get 0, which is awesome. 0 is greater than 2, not so much. 0, 0 is not a solution. Neither will be anything on this side of the boundary line. Now, I did want to make mention, and I said it before, just because x is 0 doesn't mean there aren't y values that will be solutions. For example, 0, 2 would be a solution. Right? You'd get something that says 4 is greater than 2. That would work. Or when y is 0, as long as x is like -3 or -4, that would work. So there are numbers that work, but it's that specific point and anything on that side of the boundary line that won't. So we shade on this side. You only have to do one single test of something that's not the boundary line. You're good. We're already on solving real-life problems, so I don't know if they're going to talk about the slope-intercept form stuff that I want to. I'll probably get into it during the actual solution guide if I feel it's something worthy. It is something worthy to talk about. They're big on testing points, and I get it. I will always test points to double check if I feel it's necessary. Okay, modeling with mathematics. Here we go. And here's the thing. I love not just inequality word problems, but systems of inequality word problems in the next section. I actually like these a lot. They're a lot more real life to me. You can spend at most $10 on grapes and apples for a fruit salad. See, you don't have to spend exactly $10. You can spend at most $10. I like that. Grapes cost $2.50 per pound and apples cost $1 per pound. Write and graph an inequality that represents the amount of grapes and apples, you can buy. Identify and interpret two solutions. You have to keep in mind that there is an infinite number of solutions, in a way. Unless you can only get integer values and only positive values, things like that. But here's what we're going to do. Come up with the inequality. It's not an equation, but if you need to think of it like an equation first, go ahead. $10 is the most we can spend. Boom. And then we say how many, let's see, are they using X and Y? They are. Let's let X represent the number of grapes. The number of pounds of grapes. So $2.50 per pound times the number of pounds, $2.50 times X, plus 1 pound, $1 per pound of apples times Y pounds of apples. And we aren't going to do equals 10, but less than or equal to 10. We can spend at most $10, so the amount that we spend can be less than or equal to it. So they say this. They say graph this equation, or of course you can also rewrite it in slope-intercept form. And here's their equation. Because it also includes, less than or equal to, we will have a solid line. Now, part of this stuff here, they say restrict the graph to positive values, and I agree with this, right? We can't buy negative pounds of grapes or apples. So first quadrant stuff only in our word problem. Now, when they test a value like 0, 0, you'll notice that 0, 0 becomes a true statement to this. It's a solution to it. So 0 is less than or equal to 10. It works. Therefore, we would shade on this side of the boundary line. But we're only going to be in the first quadrant. So these are the only things that can represent solutions on the line and within the first quadrant somewhere on the line. Now it said choose two solutions and interpret what they mean. Remember, anything that's in the shaded region or on the line will be a solution. So they chose something in the shaded region, 1, 6, and something on the line, 2, 5. This means you can buy 1 pound of grapes and 6 pounds of apples and be under $10. You can buy 2 pounds of grapes and 5 pounds of apples. You can be at $10 with that. Anything in here will keep you at or under $10. That's what this set means. And that's really cool. It doesn't have to be at $10. It can also be less than. You can buy nothing and you still worked itself out, right? So that's kind of what those things are saying there as far as interpreting goes. Okay, that's it for the lecture portion. Now I sat here thinking, because I don't look at these beforehand. I sat here thinking there's something I want to state a lot more on slope-intercept form, though I can't say equals anymore, but mx plus b. And it has to do with the less than. So if you remember on number lines, less than is left and greater than is right and things like that. There's something about shading above or below the line based on less thans or greater thans. I feel like if we hit slope-intercept form, I'll talk about them. And then maybe I'll do some rewrites of them. But for now, we're going to start some standard form stuff. Before that, vocabulary and core concept check. Let's go ahead. Number 1, how can you tell whether an ordered pair is a solution of a linear inequality? Well, when you substitute it into the inequality, do you make a true statement? It depends on if a true statement is made when substituting for x and y, then it is a solution. Now, the troublesome part is I need to strictly say if it is a true statement, right? I can't say if it equals it. I can't say if it's less than it. It depends on what kind of inequality they gave us. The inequality might say less than, it might say greater than, it might say, greater than or equal to. So we have to say whether or not a true statement's made, period. Number 2, compare the graph of a linear inequality in 2 variables with the graph of a linear equation in 2 variables. Well, a linear equation in 2 variables might be void of 2 other things that the inequalities will have. Linear inequalities will contain a shaded region, and it may contain a dashed line. So a linear inequality will contain a shaded region, half plane. I've never said the phrase half plane. I'm not saying they're wrong. I'm just saying that's not part of my jargon, part of my vocabulary. And it may contain a dashed line if the inequality is this or that. So an equation will not have those. You see, an equation, we might still not understand what it is that we're doing when we're drawing a graph. Oh, yeah, you plot the slope in the y-intercept, or you plot the y-intercept and you do the slope and stuff. That's great. But do we understand that all those points on the line plus the ones that we make to connect the line represent solutions to the equation? That's all they are. The line is a representation of all the solutions that make the left side equal the right side. That's all that you can do in any equation, is just have points on the line. Inequalities can maybe have points on the line if it's also equal to. Otherwise, it represents a boundary line for something that's above it for what may be solutions, or in some cases that's below it that represent the solutions. And many more solutions to come with that. All right, guys, I'm going to go ahead and get started on the problem set. We have numbers 3 through 45 to do. So a lot of graphs to be had. I'm going to go ahead and get ready. Get ready. Before doing graphs, we're going to do what they did in their sets of examples, which is testing points. Tell whether the ordered pair is a solution of the inequality, and we will, of course, be writing these ones out. X plus y is less than 7 is the statement. 2, 3 is our ordered pair to test. Let's see if 2 plus 3 is less than 7. That's 5. 5 is less than 7. That checks out. So is it? Yes, it is. That is a solution. Number 4, x minus y is less than or equal to 0. X minus y is less than or equal to 0. We're going to test 5, 2. 5 for x, 2 for y, and that's 3. 3 is not less than or equal to 0, neither nor, so this is a no, it's not a solution. Now, when we do our graphs, such a tested point would also state that no point on that side of the boundary line, assuming we graph the boundary line properly, that no other points on that side would also be solutions. Therefore, our shading would be on the other side of the boundary line when we get to that stage. But if it is a solution, we would shade on the side of those points. And of course, that's where I'm going to do a lot of testing of 0, 0, assuming that 0, 0 is not actually on the line itself. Test something small always if you can. This is negative 9 plus 6. And we have to be careful. This is negative 3. Now, is negative 3 greater than negative 2? It's actually not. It's actually less than, right? Larger negatives are smaller. So this is a no case here. Nope. Nope. There we go. Number 6. They try and get trickier with negatives and such. We'll see how they do. So number 6, we'll see how we do. Negative 6x plus 4y. Notice how all these are in standard form. That's not good nor bad. It's just notice how they're all in standard form. And for all the things I want to state about slope-intercept form, I want to make sure to stress that it will only be about slope-intercept form when I'm talking about it. Because x and y are on the same side of the equation, there are 2 variables in play, literally, no pun intended. We have to recognize that anything I talk about with slope-intercept form may not apply to standard form stuff. Anyway, 6 is less than or equal to 6. Yeah, it might not be less than it, but it is equal to it. So yes, that should hold up. 18 minus 12, 6 is less than or equal to 6. Okay. Okay, give me one sec. I have a little sound coming out of my computer here. Sorry, I have a faulty hard drive, and sometimes it does some clicking unless I do something to it. Okay. Oh, you know what I just noticed? Hold on. That was number 7. Give me a second. I think I skipped number 6. So that's what happens when I talk. I actually, honestly, I almost skipped number 4. on my problem set, and then I just realized. So I did skip number 6. So let's go back to number 6 and do that same thing. Now that one's 7. We'll go back. So number 6. All right, 8x plus y is greater than negative 6. Hope that hard drive doesn't fail. That's the only important part. Should back everything up. Okay. Now, in contrast to number 6, to number 7, here we have negative 6 is greater than negative 6. Not a true statement. Whereas 6 is less than or equal to 6 was a true statement. So the or equal to is what made this one true versus not true. When we start doing our graphs and we hit our, let's see where he did number 7. We do our boundary lines, a point on a solid boundary line will make a true statement, whereas a point on a dashed boundary line will not. And once again, that's akin to our open versus closed circle thing. It's not that the dash itself doesn't actually mean anything, meaning, oh, parts that are actually shown are good and parts that are broken aren't. No, it's just a representation of the fact that points on the line don't work. And that's the same thing for the open circle versus a closed circle. All right, this is negative 3 plus 5, and the same kind of thing as before. This becomes 2. 2 is greater than or equal to 2 is true, and that 2 is equal to 2. If it just said 2 is greater than 2, big fat no. Number 9. We have negative x minus 6y is greater than 12. So this is the opposite. Oh, we got to substitute negative 8 and 2. So this is the opposite of negative 8 that substitutes, and then minus 6 times 2 here. So that's 8 minus 12. Is 8 minus 12 greater than 12? Heck nah. Negative 4? Heck nah. Nope. Not true. And then number 10. See, I could have done these for 45 problems. It would have been kind of boring, but would have been quick. Now we got a graph and stuff, right? All right, number 10. Negative 4x minus 8y is less than 15. Let's try out negative 6, 3. And, none of the times did they try out 0, 0. I'm going to keep stressing that that is what I'm going to try for the most part. And whenever they're in standard form, it's really nice. When x and y are just 0 like that, that means the whole left side is just 0. It can be very, very easy to compare. So 24 minus 24. Well, that's 0. But also, it's less than 15. Yeehaw. So yes, negative 6, 3 is a solution to said inequality. We shade on said side. Okay, numbers 11 through 16 say, tell whether the ordered pair is a solution to the inequality whose graph is shown. This is going to be pretty straightforward, guys. On these problems here, and honestly, I don't do this very often, but I'm going to copy and paste. Hold on. I'm just going to copy and paste this whole set right here because right underneath, I can write yes versus no. I hope that's okay that I'll do this, including the graph, because we can just plot the points and see if they're good. This is literally a test among, we already have the shaded region there, but I guess part of the point of that is because we also don't have the original inequality that was written. The inequality is actually y is greater than x. So as long as the y value is greater than the x value, then it will be good. Anyway, so for number 11 on 0, negative 1, that is this point right here. I'm going to make it red when it's a no. It's not a solution because it's not in the shaded region. Number 12 is negative 1, 3. Well, the y is greater than the x. I mean, also it's in the shaded region, so that is a yes. 1, 4, the y is greater than the x, and of course we're going to see that also in green up here, so that's also a yes. Sorry if I don't switch these things over. 12, 13. Number 14, 0, 0. Now, this is not one I would test on this kind of one because 0, 0 is on the boundary line, but for our test of it, it's on a dashed portion of the line, so it's also a no. If it's on a dashed portion of the line, no, it's not going to work. Number 15 is 3, 3. Should also be on the dashed portion of the line. Again, if this was a solid line, we'd be good. If it's on a dashed line, no good. So also a no. And then 16, 2 is the x, 1 is the y right there. Also underneath in the shaded region, also a no. So we got several no's going on there. A couple yeses. We generally don't do it that way. Generally, we need to find out what side to shade on and go from there. But if we were asked to pick solutions, you could understand which ones to pick. Something above the shaded region, the boundary line. Okay, numbers 17 and 18 are word problems. A carpenter has at most $250 to spend on lumber. The inequality 8x plus 12y is less than or equal to 250. Represents the numbers x of 2x8 boards and the numbers y of 4x4 boards the carpenter can buy. Can the carpenter buy 12 2x8 boards, that's x, and 14 4x4 boards, that's y? Explain. Well, this is just through a substitution. They say the 4x4 boards are by 8 are $12 each, and these are $8 each. That's why the inequality is written the way that it is. Now, they made this one for us. Later, we're going to write some for our own, right? This is a straight substitution. It is coming off the last problems that we did. So far, we're still not graphing ourselves. This book is very good, and it's very good at making a progressive system out of these. 8 times 12 is 96. 12 times 14 is 168. So is this less than or equal to 250? I don't think so. I think that is 262. Help me out there. 262. 262 less than or equal to 250 is a negative Ghost Rider. So can the carpenter buy this many? No. No. 260. It would cost $262. Too pricey. Too rich for my blood. Not in my budget and expenditures. Number 18. The inequality 3x plus 2y is greater than or equal to 93 represents the numbers x of multiple choice questions and the numbers y of matching questions you can answer correctly to receive an A. So it sounds like we need to answer a certain amount correctly to get 93% or more, right? That's the idea. You answer 20 multiple choice questions and 18 matching questions correctly. Do you receive an A on the test? Explain. So that's a nice version of representing inequality word problem-wise, something that we can all relate to as students or teachers or whatever. So we're going to test this with, multiple choice is x, so 20 is how many we're going to get correct there, and 18 for y. So let's see if we get at least that 93 or more, and at least 93. If it's 93, we'd be good. And this is where that mix and match really comes from, right? Maybe you answer more multiple choice questions, but less free response questions, and you can still get it in comparison to this. So this is going to be 96. 96 is greater than or equal to 93. So yes, you'll be good in this case. Yes, because this is a solution to it, you would receive 96%. I'm assuming these are percentages. Maybe that's faulty to assume, but I did it. You can't stop me. Okay. It sounds like it, right? 93 is an A, that kind of thing. Okay, numbers 19 through 24 says graph the inequality in a coordinate plane. Now, these ones very specifically are just one variable, which is interesting because we're still doing them on the same, we're not doing it on a number line, right? Y is less than or equal to 5. So here's the idea of these, and I have to get graph paper, or graph axes. You have to get graph paper. Y is less than or equal to 5. Our idea for these problems is we will be graphing the boundary line y equals 5 to begin with. Now, y equals 5 would be a horizontal line. Make no mistake, it is a horizontal line. It is at 5. Whether we do it dashed or solid is based on whether it can also be equal to. In this case, it can. It can also be equal to. So for y's, I'm getting it set up, sorry. I'm setting up all my different parameters I need because my shading is going to be different. Y is less than 5. What I want to do for this set is I want to test a point here. I'd like to test 0, 0. This point right here. Will this be a solution to this or not? Now, this is by asking, is 0 less than or equal to 5? I substitute 0 for y, nowhere to sub 0 for x. That is true. Therefore, anything on the side of 0, 0 will also be a solution to this. So anything under the line. And this is where I would do the shading. My shading is going to look different from yours, given what I have here as a tool. But this will be my shading of that. So 0, 0 works. Anything below works. Now, later I'm going to try and start making sense of how these things work when it comes to shading above versus below, things like that. It's not always above and below, though, because we'll have some where we compare x's. But that one's good. All right, there's number 19. Let's go to number 20. Y is greater than 6. Now, in y is greater than 6, what we have to understand is, once again, boundary line will be graphed, y equals 6. However, in this case, the greater than does not include the or equal to portion. So if it doesn't include the or equal to portion, that means this line is not solid. It will be dashed. And a dashed line, and what you would do with, honestly, what I would do with you, what you should do is one of two things. Either draw the line and use the eraser and just erase little parts of it, or use a ruler, and when you draw that line, really, dot, 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 kind of hit dots on it. Now, y is greater than 6. If I test 0, 0 this time, you'll notice it says 0 is greater than 6, and that's no good as a statement. Therefore, nothing on this side should work, including 0, 0. So anything only greater than, above 6 for those y values should work. And that makes sense to us. So we're going to be shading above. That means points on the line don't count. 0, 6 don't count. 2, 6 don't count. 8, 6 don't count. Negative 4, 6 don't count. Only things above it when the y is greater than 6, including 6.1. Doesn't matter what x is. Doesn't matter what x is. Not for the one variable ones. We're still graphing them on a number, on a set of axes, though. Numbers 21 and 22 involve x this time. X is less than 2 is the first one. So with this one, an x equals equation, if you recall, is a vertical line, not a horizontal line. So x equals 2 would look like this. Because it's less than and not equal to, it will only be a dotted or dashed line, not a solid line like this. And really, listen, test a point like 0, 0. That does mean 0 for x. You plug in 0 for x. 0 is less than 2 is a true statement. Therefore, anything on the side of 0, 0 would work, which is this side. So we will be shading to its left. Now, that should ring a lot of bells to what we did on number lines with x's at the time, right? Number lines go left and right. If I graphed x is less than 2 on a number line, what would I do? I'd put a boundary point on 2, and I'd shade to the left. Left, less is left. That's for x's, right? Y, down is, or less is down. But yes, if I graphed x is less than 2 on a number line, keep in mind what that would look like. Once again, it would look like a number line. Here's 0, here's 2. We would do an open circle, and we would go to the left. This looks a lot like this. Here's the open circle equivalent, and here's the going to the left. The difference is you can be any y value meanwhile. And that's kind of how this thing works, right? Kind of how this thing works. So if we're understanding this, and maybe we don't need to test points like out loud. When I say out loud, I mean like by writing it down. Or we're starting to understand the less thans and greater thans. Maybe we can work it out for this problem. X is greater than or equal to negative 3. First of all, means a boundary line on negative 3, and it's a vertical line for x. It's solid because it also includes negative 3 for x, so anything on the line does count. If x is greater than negative 3, greater than's to the right when compared to x's, so we will graph to the right of this. You can also test 0, 0. 0 is greater than negative 3, so that will work. So anything to this right side will work as well. Apologies if it looks like it leaks over. I can't color inside lines with this tool. I would do very light shading with your pencil, especially when we hit systems of inequalities in the next section. So I can try and do versions of that, but I don't want, I'm already going to ruin, this thing's going to get ruined over time for sure. I always question how I want to do these things logistically on a computer, and sometimes it's tough. All right, back to y again. Let's see if we can now make a little more sense of it here. We got y is greater than negative 7. Now keep in mind, y kind of compares upward and downward. Even though this boundary line's a horizontal line, we state what's above, what's below, right? So negative 7 is down here in a y equals format. It's only greater than, it's not equal to, therefore a dashed line is in order. Y is greater than, 0 is greater than, 0 is above, therefore anything above will count, and that's what we're going to do. Anything above right here, including 0, 0, or 0, anything for y that's 0. Anything for x when y is 0, I should say. There's our wonderful shading of this graph. You missed a spot. There we go. Okay, and then number 24, x is less than 9. Oh, we really got a lot to shade there. You know what I should do for these ones, because they are just vertical and horizontal lines? Let me show you. I'm going to do something different on this one. I'm going to shade the same way, but x is less than 9. There's a vertical line on x equals 9, and because it is not also equal to, we will be doing a dashed line. Now, here's what I'm going to do this time. I'm going to use the rectangle tool. I'm going to lighten up. Let's see what this looks like. So less than 9 is on this side of 9. There we go. There's my shading. So shading to that side of 9 to the left of it, including something like 0, 0, works out on that. Okay. In exercises 25 to 30, graph the inequality in a coordinate plane. Now, as I'm just going to call it out as it is. The first two problems are in slope-intercept form. The next problems after are in standard form. The majority, except for number 30, honestly, the majority of all these standard form problems, guys, I almost want to write in slope-intercept form anyway, just because I'd leave myself with fractions in standard form. So I am going to get to talking about a little trick that you can use that you might have noticed in the previous problems with the shading without actually testing a point. That being said, I will be testing 0, 0, especially to begin with, and it ain't too bad to test. 0, 0 is a pretty straightforward thing. All right, y is greater than negative 2x minus 4. This means we will be graphing the boundary line y equals negative 2x minus 4. That means y-intercept of 4 and a slope of negative 2 like this. Now the boundary line will either be solid or dashed based on whether it's also equal to. This one's not also equal to, so eventually I will make this one dashed. I'll start solid because that's just how my tool is beginning. And then I'll transform it into a dashed line, just like how you can erase parts of your line. Kind of up to you. Dashed line there. Now, if I tested a point such as 0, 0 right here, here's what it would look like. I will test to see, is 0 greater than negative 2 times 0 minus 4? Is 0 greater than negative 4? Yes. Therefore, 0, 0 works. Therefore, any point on this side, I could test 5, 3, that'll work. I could test 2, negative 5, that'll work. I could test negative 3, 3, that would work. Anything on this side would not. This is where I got to actually do my shaded region stuff again. So, let me get the right tool. And, whoopsies. Anything on this side works, including 0, 0. So, we all good there? Yeah, I'm going to destroy the tip of my pen by doing this. This is not good for it at all. Okay, so that's what this graph looks like. That's it. Now, I'm going to start making mention of this now and see if it starts to click later, okay? This is slope-intercept form. That means y is by itself. If you saw when y was by, well, this is x, but if you saw it when y was by itself in previous problems like this, when y was greater than, we shaded above. When y was less, oh, that's y. Y is greater than, we shaded above. When y was less than, we shaded below. When y compares to whatever's on the other side, we shade above versus below when it's greater than or less than. That's important because slope-intercept form does that. So greater than, we shade above. Now, what does above mean? That means at any point, like this x is negative 4. At this point, shading above is up here, above it. This is shading above and shading above. The way that I make it akin, or I talk about it in class is if I had a, if this was like a sim video game thing and I could pick up a boy and drop him down on the water, or like on the slide, whee! If he fell down right now, straight down, would he slide safely? Yes, he would. Whee! Here I go. It's a steep slide, I get it. If I put him over here and drop him, and he's gone, right? Right here. Is he above the slide? No. Is he above the slide? Yes. Wee! Like that, right? So above versus below. Doesn't matter how steep it is. This is not about left and right when you compare y. So that's something I want to start stating, and I'm going to start connecting that. So after the first two problems, sure, I'll test 0, 0. All will be good. But I really, the book's not stating it. I don't think they stated it even for number line things. Less is left, greater is right, right? They didn't do that at the time. So same thing here. Y is less than or equal to 3x minus 1. This is in slope-intercept form, so not only do I graph with the slope and y-intercept and such, but I can also shade above versus below based on whether y is less than or greater than. So this boundary line looks like this, a slope of 3, y-intercept of negative 1. It is solid because it's also equal to. So here's the solid boundary line, and on one side of this boundary line, points will work. On the other side, it will not. Now, 0, 0 is not on the boundary line. It's just above it. Will 0, 0 work as a solution? Without actually testing points, just look at the less than. If y is less than below or above? Less than is below when y compares to it. I need to stress this. This is when y is by itself. Okay? So what's below? Well, think of the boy. I erased the boy from existence. If I drop the boy right here, he's above. Whee! If I drop him below, he's below. So below should be the area I should shade. Let's test 0, 0 and see if that works out. Here's 0, 0 right there. Is 0 less than or equal to negative 1? No, it's very close to it, and that's why the point's very close to it. But any point on this side will not work. Only points on the other side will work. Now, testing is so fast that I don't want to stop you from the idea of testing there to make things happen. That's partly why the book is also preaching it so much. But if I want to know something well beforehand and not kind of make a big deal out of it, I could also look at the less than versus greater than and tell myself whether shade above or below. Only when, and I have to keep stressing this because people are going to just say, hey, wait, you said always. No, I didn't. Only when y is by itself. When y is less than or equal to y, when we're in slope-intercept form, how that thing compares. That's the important part. And that's really important because on problems like these, 27, etc., I probably want to get this in slope-intercept form. Graphing this out of standard form wouldn't be any good given that the x-intercept would be a terrible fraction. So negative 4x plus y is less than negative 7. Let's add 4x to both sides, and it'll say y is less than 4x minus 7. I might have to sneeze here in a moment, by the way. So there's the rewrite of this thing, yeah? Now, given that it was rewritten, the inequality did stay the same, but that's how I'm going to graph it as well. Now, the less than and not less than or equal to means that this will not have a solid line, but rather a dashed line. So we're looking at this graph right here, and this line, which we have to break up into dashed little pieces. So let's go ahead and do that. All right, so there it is right there. If y is less than, we should be shading below, which means 0, 0 shouldn't work. Let's do it mentally this time. Is 0 less than negative 7? No. 0, 0 doesn't work. Neither should anything on that side, so we shade below. The area where a boy would drop to doom, which is whatever, right? I mean, you know, we want to drop the boy to doom in this problem because y is less than. The point is he wouldn't fall on the slide, and it should be a solution. Here's a solution to our problems. Drop the boy to doom. It's exactly. This is what you learned at school today, kids. Okay. Number 28. Number 28 has a little trick to this. Now, keep in mind, I would love to graph out a standard form with intercepts and such if I didn't have any fractions, but dividing 5 by 3 would lead to a fraction, so I don't really want to handle that. So 3x minus y is greater than or equal to 5. Well, then let's get y by itself. Subtract 3x from both sides, and then divide by negative 1. Here's where it gets tricky. This is positive 3x, here's negative 5. Guys, what happens when you divide both sides by a negative in an inequality? You flip the fraction. You flip the fraction. The fraction. Why did I say fraction? You flip the inequality. Goes from greater than to less than. This is a time when testing a point should absolutely be had. You rewrite something in slope-intercept form, it's great that you flip that inequality on your own or didn't. It's up to whatever you did or not. We'll graph the boundary line. I trust what I made on the boundary lines right. I've been doing that for a long time with you guys, right? The question is, should we be shading below this line, or should have I not flipped it at all, right? That's the question. I think we should have flipped it. I told you a good reason why we should have. But here's where you do your test, and here's the thing. Don't test 0, 0, even though I think I just did it on the last problem. Don't test 0, 0 to the newly written thing. Test it against the original one. Is 0 greater than or equal to 5? No. Now, if you test it over here, this will say 0 is less than or equal to negative 5. Also not true, as it should be. It should not be true because the original wasn't true. So that flip, thank goodness we flipped it. Otherwise, it would say 0 is greater than or equal to negative 5. It would have worked out and we would have all been good. This is why you still test against the original. Whether or not you write it in slope-intercept form, you should test against the original and see which way you go. If 0, 0 is not a solution, so is neither is anything on that side of it. So we've had a lot of less thans recently. Dropping a boy below the slide right here. A lot of graphs looking like this, but this is the answer to this one. Shading on this side of it, less than. Under. 0, 0 is not there. Sorry about the overlap. That has to do with my stylus tip is getting messed up, so it's going to have overlap like that. It's breaking. It's breaking. All right, number 29. Once again, slope-intercept form will be had, and once again, it appears I will be dividing by a negative to get y by itself. So we'll have 5x minus 2y is less than or equal to 6. If I subtract 5x from both sides, I will get this. And if I divide everything by negative 2, the inequality should flip. So greater than or equal to, and this is positive 5 halves x and minus 3. That's dividing by -2 there. So there's a rewrite. This is how I will do my boundary line. So my boundary line is going to have y-intercept of -3 and a slope of 5/2. So up 5 over 2, like so. This one will also have a solid boundary line. Now, will I shade above or below? It's your question as to whether you do the 0, 0 test. If I test 0, 0, I get 0 is less than or equal to 6. That means I should test on the side of 0, 0. That I should shade on the side of 0, 0. Wait, Mr. Robinson, it says less than. Aren't you supposed to shade below? No. Sorry, I don't want to yell. No, this is not. This is y right here. When y is by itself, and it's greater than or less than, you shade above or below. But you should also do the test of the original, because were you supposed to flip the inequality or not? A lot of things like that. The less than here is misleading because the y here is negative, and maybe that's something you can remember. But no, this less than is nothing more than something to test points with. Is 0 less than or equal to 6? It is. So you test on the side of 0, 0. You shade on the side of 0, 0. My words are all messed up here today. So we shade on this side like that. 0, 0, and everything thereafter. You know what? I think I have a thicker circle thing I can use. I haven't been using it. I'm going to switch to it. From here on out, I'm going to do one that's yay thicker. It's a little bit thicker. So we shade on that side, and notice this one does say greater than because I knew to flip the inequality. But if you forget to flip it, you got to do your tests. Hopefully we're learning off that. Number 30 would have been fine to do out of standard form when it comes to no fraction intercepts. However, the x-intercept here would have been 12. That's slightly out of window range. So I am, once again, going to rewrite in slope-intercept form. I'm going to add x to both sides. And I'm going to divide everything by 4. Oh, this is a y. And I'm going to divide everything by 4. Doesn't flip the inequality, of course. And we get this guy. So it doesn't flip the inequality. The greater than, y is greater than, means I should be shading above. The greater than also means I need a dashed line. So -3 up 1 over 4. We didn't really have negative x slope or negative slopes, did we? Doesn't seem like it. Maybe we get them later. Anywho, let's dash this thing up. Everyone's special dash. All right, shade above. Do we trust a shade above? Well, I don't know. Even if you don't trust it, test 0, 0. Is 0 greater than -12? Yeah. Well, then we shade on the side of 0, 0. So, again, I'm not ever going to pull you away from... Sorry, there's going to be some weird looking overlap. I'm not going to pull you away from testing 0, 0, or from testing any point. Please, please test 0, 0. It's so quick to do. Notice how I just said that. I didn't say -0 plus 4 times 0 is 0 plus 0, which is 0. I just said is 0 greater than -12. And also test with the original inequality right there to make sure you have this one drawn right. But this greater than here, if I did it right, means I do shade above the line. Boy lands on the slide. It's a nice, safe slide. We're good to go. All right, 31 and 32 on error analysis. I'm assuming one of these is going to be shading the wrong direction, and one of these is going to be a dashed versus solid line the wrong way, because that's just the right things to talk about now. So number 31, y is less than -x plus 1. Let's talk about the slope and y-intercept. All good. Boundary line's good. The shading, if we were talking about y being by itself and less than, shaded below is good. Test 0, 0. 0 is less than 1. That's good. The problem is this line is solid instead of dashed. So the line is solid instead of dashed. That's all I'm going to say. I'm not going to actually correct it. I mean, I'm not going to do an entire new thing. I can go ahead and just draw one on there if you'd like me to. But the line is solid instead of dashed, right? That's the actual issue. So, boom. All fixed. We're good. Number 32. Y is less than or equal to 3x minus 2. Again, boundary line looks good. The slope of 3 and y-intercept of -2 is great. That works out. It's a solid line, as it should be. But as we've now learned, if y is by itself in these scenarios, when it's less than, we should be shading below. A boy shouldn't be able to drop safely on the line here. It should fall down below the slide, and 2 is ultimate doom. So they shaded above the line instead of below the line. Now, for themselves, if you test 0, 0, you should get a false statement. And what would that false statement be? The false statement would say 0 is less than or equal to -2, and that's not a true statement. 0 is not less than or equal to -2. 0 is less than or equal to -2. Therefore, we shouldn't shade on the side of 0, 0. Therefore, we should shade in the region that does not contain 0, 0, which is below the boundary line. Once again, one of those things, I'm probably not going to do a whole redraw of it. What I will do, I'll just kind of do quick shading right here. They should have done it right here. Like that. Okay. Now, don't make the shading that rough, right? We want to kind of count all the points that work there. Best as we can. Okay, number 33. You have at most $20 to spend at an arcade. Arcade games cost 75 cents each, and snacks cost $2.25 each. Write and graph an inequality that represents the number of games you can play and snacks you can buy. Identify and interpret two solutions of the inequality. You want to use X and Y because we're going to do things on graphs. So X is number of arcade games, not just X equals arcade games that you can play. Y is number of snacks you can buy. So let's write an inequality based off that to begin with. We're going to have 75 cents. So 0.75x plus 225y. We can spend at most $20. So we have to stay less than or equal to $20 as a whole here. To 75, I'm going to check something on my calculator here. No, it doesn't divide evenly there. I was going to go for, what do you call it? Graphing out a standard form. Let's graph out a slope-intercept form here. Even then, we could use the graphing calculator if we wanted to. That would be kind of nice. So here, let's get y by itself. So 2.25y is less than or equal to, let's subtract that over, negative 0.75x plus 20. When we divide by 2.25, see, I think that's 1/3. 0.75 divided by 2.25, yeah, that's 0.3 repeating. So when we divide by that, that'd actually be negative 1/3 x plus, and I think this is, no, that's not, oh, yeah, this isn't a great number. I thought it was 250. So that's 8.8 repeating. So what's that fraction? I should know that one. 89ths, wow, plus 89ths. I have no good way of representing that other than that. So there's the graph, sure. Or that's the inequality. If I graphed it, I'm gonna go ahead and use the graphing calculator for it. It's just so we can talk about solutions. Negative 1/3 x. Now 89ths was around 8.8 something repeating, right? So just make sure that we know that. We're gonna use the first quadrant only. I don't care about the other quadrants there. Let's see what this looks like to start with. Keep in mind, this is just a line. Okay, that's gonna extend farther. Let's make x's go farther out to $20 to spend. If I go out to 20, will it fit then? Is that fine? No. Oh, because the games are 75 cents each. That's right. Just go to 30. So here's the other thing, right? This is just a line. We can talk inequality stuff, or I can shade it on my own. But this thing has the ability to do shading. We should shade below because it is less than or equal to. So if I hit enter a couple times here, that's shading above. That's shading below like that. So I do this graph here. That's an understanding of that inequality as well. So I can get this thing to do it. Now, my graph window, because they said choose a couple points, right? They said identify, interpret two solutions. So I'm going to copy that and paste it in here. So if I identify a couple solutions, that is the graph. Maybe I cheated a little bit, but they gave me bad numbers. So don't give me bad numbers and I won't cheat a little bit. So what are some points on here? Well, this goes to 30 and this goes to 10. So I'm just going to do the best I can with like kind of making ones up. I'm not going to get on the line itself. Let's do something like, I don't know, 20,2. 20,2. I think that fits. And let's do something like, you know, I don't know if this is 4 or not. I'm just going to make it up. 4, 4, like that. So 20,2 and 4, state you can afford to play 20 games and buy 2 snacks. And also you can afford to play 4 games and buy 4 snacks. Now 20 games would run you, I think, $15. 20 games is $15. 2 snacks. Ooh, that would be really close. That'd net you $19.50. So the two snacks is probably a little higher up. The 20 is probably a little further over. So this thing was probably going to be a little more like that. But yeah, 20 games and 2 snacks pushes you pretty close. It's $19.50. 4 games and 4 snacks doesn't really run you that much. Just a little more than $10. Okay, that's kind of what that's looking like there on number 33. Number 34, a drama club must sell at least $1,500 worth of tickets to cover the expenses of producing a play. Write and graph an inequality that represents how many adult and student tickets the club must sell, identify, and interpret 2 solutions of the inequality. So on this one, adults are $10 each, students $6 each. Let's let X equal number of adult ticks and Y equal number of student ticks. And this says 10x, we can say 10x plus 6y must be greater than or equal to 1,500. We have to exceed it. Now, this is one where I can at least do intercepts on and be okay. Remember, we first graph the boundary line as if it's equal to. So for our x-intercept, if we divide 1,500 by 10, we get 150. The y-intercept, if we divide 1,500 by 6, we get, I don't know, I just know it's a clean number. 1,500 divided by 6, we get 250. So these are our x and y intercepts. If I kind of made up my own graph based off that, it would look like so. This time I'm not going to use a graphing calculator just because I don't have to cheat this time. But it would look like so. We could do 2 Schwede and 1 Schwede. Now this time I actually even graphed out a standard form, right? I'm not using slope-intercept form. Now the thing about this one is, how do I say this? Let's see. First of all, we'll still stay in the first quadrant. We will be a solid line. I didn't rewrite it in slope-intercept form, but we will shade above. If I test 0, 0, 0 is not greater than 1,500. 0, 0 is on that side, so we will be shading above in this case here. So anything above on these sides would totally do. That means something above right here and above right here, something on the line. And I don't know what's exactly on the line. I'm going to have to be careful with that. So I just got to make up some ones that would totally work out in this case. We could work out something like, 100, 200, I'm going to guess is going to work just fine. And 150, I know anything at 150 or more is going to work. So 150, 10 will work. So you need to make at least $1,500. 100 adult tickets and 200 student tickets should do that. You'll get about $2,200, I think, on that. And then this one here, 150 adult tickets and that means student tickets, I think gets you $1,560. So if you sold, let's see, you will cover 1,500 if you sold 100 adult ticks and 200 student ticks, or if you sold right. So that's just the idea. Okay, it's just, there's an infinite number of solutions. There are ones that are on the line that'll also work, but since I didn't get exact points from them, the numbers are kind of big. I'm just going to leave it like that. But that's how it looks. All right, let's go to numbers 35 to 38. Write an inequality that represents the graph. Interestingly enough, this is where the things that we spoke on greater than and less than, things like that, will work out, especially since we have slope-intercept form to play with. Now, I am going to copy and paste these graphs over to just talk about slope and y-intercept. Those are the parts that we need. So here's the initial graph. I have a y-intercept, a b value of 1. My slope is, pick another point, it's my rise and run. Rise 2, run 1, my slope is 2. So my equation would initially look like y equals 2x plus 1, but not so fast. We have to talk about shaded versus dashed, or solid versus dashed. Dashed means it's either going to be this or that. Which one? The shading is above. Because we're in slope-intercept form, shading's above means will be greater than. You can double check this by testing 0, 0. Is 0 greater than 1? No, so nothing on the side of 0, 0 will work. Therefore, that is our inequality. Number 36. Same-ish. Literally, quite. It's a different boundary line, but what do we have? We have a dashed line and we shade above. So I think greater than will be in order once again. How do we compare y to the, right, to this thing? We have a y-intercept of 2 and slope of up 1 over 2. So m is 1/2. This will be y is greater than 1/2 x plus 2. And it's still greater than, once again, because dashed line and we're shading above. 0, 0 doesn't work. 0 is not greater than 2. Number 37. Our line is solid. Solid line on number 37. My neck and back and stuff are really bothering me. If you see me do a lot of stuff like this and stuff, I've had a lot of issues in the past few days. So sorry about that. Number 37. We have a y-intercept, I'm just going to say these out loud, of -2 and a slope of -1/2. So this is y compared to -1/2 x minus 2. However, this time, solid line, that means also equal to, and we're shading below it, so y is less than that. 0, 0 would state 0 is less than or equal to -2, not a true statement, therefore that wouldn't apply. So that's our answer. Number 38. Also a solid line and also shading below the line. A boy on the shaded region when dropped would not land on the slide. Poor little boy. Poor child. Should have had a different inequality. Speaking of which, we got to write it out. Y-intercept of -3 and a slope of +3. Up 3 over 1 looks to be the case. So y and 3x minus 3 going on there. But we are shading below, and it's also including the boundary line. 0, 0 doesn't work. 0, 0 didn't work on any of these ones. Boo hiss. Okay, number 39, problem solving. Parts A and B. Large boxes weigh 75 pounds, and small boxes weigh 40 pounds. Write and graph an inequality that represents the numbers of large and small boxes a 200-pound delivery person can take on an elevator. The weight limit is 2,000 pounds. We cannot exceed 2,000 pounds. We must be less than or equal to it. The weight of the 200-pound individual also has to be factored into this. So if X represents the number of large boxes, I'm not going to define them in writing, I'll say it out loud. They weigh 75 pounds each. And small boxes weigh 45 pounds each, and we had Y amounts of those. Here is our inequality. This will be the start of part A. So let's write a part A there. It said write it. And said graph it. So in order for us to graph it, let's do some rewriting of this. I'm going to subtract 200. All of these can divide. Was that the case? You know what? Let me go back to that student adult one in a sec. The tickets one. I could have divided everything here by 2 and made it a little bit smaller. I probably should have. Now, granted, I worked toward intercepts. This way I can probably also work toward intercepts. 75 may go into 1800. 40 should as well. But let's divide everything, just for a moment, let's divide everything by 5. Divide everything by 5, make it a little smaller. We get 15x plus 8y is less than or equal to 360, I think. And yeah, just as far as this goes, yeah, 15 goes in 360. And 8, I think, also goes in 360. So when it comes to stuff, I'm trying to think about whether I should use the graphing calculator or not. Sorry, I'm thinking out loud. I just, when it goes to stuff here, I'm just going to do x and y intercepts, and we'll do a generic graph. The x intercepts, you divide 360 by 15, and you get, I think, 24. Y intercept, oh, I got to check if that divides right. It should, because 450, it should be 45. Let's see, 8 times 45. Yeah, I knew that. So 45. Okay, so those are our intercepts for this thing. So in a generic graph format, we will have this going on. X-intercept of 24, Y-intercept of 45, totally not to scale. Sorry about that. Maybe we should shift that 24 over a little bit. Like so. And then we draw the lines that goes this through. Maybe like that. Now, it must be less than or equal to the 360. Well, I mean, everything that we wrote has to do with that. 0, 0 would be included in a solution set, meaning if you carried 0 boxes on there, you would be underneath the weight threshold, which is all, which is gravy. That's good. I'm going to thin out this one a little bit more like that, but any of these represent solutions. So anything on the line is solutions. Anything underneath the line within first quadrant stuff are solutions to this thing. Anything above is no. Explain why some solutions of the inequality might not be practical in real life. You might not be able to fit that many boxes in the elevator, is probably my guess. I don't know specifically what they want to state here, but even if, say, 45 small boxes can fit in the elevator, the person might not be able, not fixing the elevator, can apply, can be taken on the elevator. The person might not be able to load 45 boxes on there, or they might not fit volumetrically, like in terms of space, right? That's my idea. Even if they are solutions. Oh, that's probably not what they meant. I totally take this back. Okay, if they meant that, great. Okay, here's what I'm thinking now what they probably meant. They're probably talking about decimal answers. You can only have integer amounts of boxes. So a solution... Now, this would have been the case for the arcade games, right? You can't play 4.5 arcade games. But so a solution like, 2.5 large boxes and 18.1 small boxes wouldn't apply. So I don't know which one they meant. I was thinking practically here, and here I was thinking just, mathematical. It's just an either or kind of thing. So I don't know which one they meant. I'm just going to write both. That's thinking. Outside the box. The small box, the large box. That's thinking. All right, how do you see it? Number 40. Match each inequality with its graph. Okay, they all have 3x minus 2y, so the intercepts themselves ain't the thing in play that we're talking about. What I'm going to do is rewrite just one of them. Just one of them, and I'm going to do that first one. I take it back. We're going to test 0, 0. We're going to test 0, 0. We're going to apply to what they do. First of all, less than or equal to, all the things. The inequalities are all presented here. Solid lines are going to be the ones that are also equal to, so B and C will apply to this, A and D somehow, things like that. So on A, your 3x minus 2y is less than or equal to 6. If I test 0, 0, then 0 is indeed less than or equal to 6. So I'm looking for the solid line that includes 0, 0 on it. That would be C. Solid line, it includes 0, 0. It's gonna be C. Part B. Oh, my neck, my back. 3x minus 2y is less than 6. Now, 0 is also less than 6. That works out. The difference is this should be a dashed line. So we're going to look at A for that. 0, 0 is included, but a dashed line is there. So part B will be graph A. Part C and D really is just by process of elimination now based on the solid line versus dashed lines, but let's still do tests of 0, 0 to ensure that what we're talking about still holds. If I test 0 here, it says 0 is greater than 6, which ain't true. So therefore, it won't apply there, and it should be a dashed line. So 0, 0 isn't on there. Like that is D with the dashed line. And then the last one should be B, but let's do a double check of that. 3x minus 2y is greater than or equal to 6. 0 ain't greater than or equal to 6. It ain't either. And it's a solid line on there, so B applies to that last one. So no rewrite in slope-intercept form for that one. They have great intercepts, and they're already graphed for you. It's just a matter of testing points. Number 41. When graphing a linear inequality in two variables, why must you choose a test point that is not on the boundary line? Well, yeah, so, right, we don't test 0, 0 if 0, 0 is on the boundary line because that's not a test for which side we shade on. We're trying to decide our boundary point test, or our test point is to determine whether that region, they say half shading or whatever, whether that region is contains our solutions. A point on the boundary line doesn't dictate this. This is the same thing as number lines. Why I would always test 0. It's an easy test, but also if 0 works, we shade on that, or we draw arrow on that side. If it doesn't work, we do on the other side. It's also why we don't test boundary points there. That's why I said if my equation said x is greater than 0 or something like that, I'm not going to test 0 because 0 is the boundary point. I need to test something on one side or the other, like 1 or -1 or whatever. And those are pretty easy to test. So if 0, 0's on it, test 1, 0, right? Test something that's really close, really easy to calculate. Number 42, thought-provoking. Write a linear inequality in two variables that has the following properties, where these are not solutions and yet these are solutions. What would be nice for us to do here is plot these on a graph and then make something out of it from there. It's hard to picture it unless I see them actually work out. So I need 0, 0. I'm going to plot them in green if they work. 0, 0, 0, -1, and 0, 1. These are solutions. And yet 1, 1, 3, -1, and -1, 3 are not solutions. So I could do something like, if I'm parallel to these points here, that slope looks to be -1. If I'm parallel to it and give like a solid line on this, this would work out. So let's do something like this here. I'm going to change, hold on. I'm going to make it a solid line. I'm going to have a slope of -1, but I'm going to rummage from up here and downward. So let's see. I want to make sure that it does work. So like that. This one would work here as long as I shade underneath. So let's actually make it blue, not green. Like that. And then we'll shade underneath. Give me 1 sec. I'm getting all my pen tools right because we haven't been doing shading for a while, and I changed some of my settings. Almost done, almost done. Okay. All right, so let's shade on this side of it. Okay, so this is the equation, the inequality that I'm going to make to kind of assure that it works right. Assuming that I plotted those points right, I believe I did. So those should all work down there. Now this equation is y-intercept of 1, slope of -1. And I'm shading under, and I include those points. So y is less than or equal to -1x plus 1 is the one I'm going to go with. Oh, I have the things backwards. I didn't even see that. Guys, time out. These are solutions. Those are not solutions. Wow. How did I totally miss that? Okay, hold on. Let's do that again. Okay. These. Wow, 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 wow. Wow, 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 wow. Sorry about that. Same idea still applies. Flip it over though, right? So these three, not solutions. That being said, I don't want this to be solid anymore. Dotted. Okay. Hey, guys. This, well, listen, the line is still the same. All I got to do is flip this thing over. You know what would help? If I did those the right way. That's what I should do. Okay. Totally works that way. I could have also done, now that I see I could have done these, I could have gone one up and I could have made I could have also done y is greater than or equal to -x plus 2. If the y-intercept's on there, then these are actually on the line like that. So this also would have been a good one. Sorry about that. Fixed it. Okay, number 43. Can you always use 0, 0 as a test point when graphing an inequality explained? No, because not if 0, 0 is on the boundary line. You cannot test 0, 0, although I would then test something like 0, 1. You cannot test 0, 0 if it is on the boundary line. Instead, test something like 0, 1 or 1, 0 or something like that. Make it really easy for yourself. Okay, number 44 and 45, last two questions. Write and graph an inequality whose graph is described by the given information. So these points lie in the boundary line, and these points are solutions. Okay, so this is kind of like number 42, only now we have to construct the exact boundary line that they have. So boundary line contains the points 2, 5, and -3, 5. -3, -5. Let's start that by using kind of point slope form-esque stuff. So we can come up with our slope first of, say, y2 minus y1 over x2 minus, minus x1, which is 10 over 5, which is 2. And then we go ahead and plug in a set of points like these ones. Y minus 5 equals 2 times x minus 2. We distribute the 2. Keep in mind, I'm only doing the boundary, and I add 5. I'm only dealing with the boundary part to begin with. So 2x plus 1. That's the boundary line. Now, when it comes to the graph, I'll draw the boundary line, and then let's see what side the solutions are on so we can decide whether we shade above or below for that. So 2x plus 1. And keep in mind, that should include the points. What were they? 2, 5. It should include the points 2, 5, and -3, -5. And if I do 2x plus 1, it does that. Up 2 over 1, up 2 over 1. Boom, it hits it. Up 2 over 1, up 2 over 1. And boom, boom, and boom, it hits that one. So it does seem to apply, given that slope and that y-intercept. So I don't know if I'm kind of required to do the point slope form stuff like that or not. Now, I don't yet know if the points that they test are on the line or not. So let's see what points they're talking about. They say 6, 5, and -2, -3 are solutions. So 6, 5, I'm going to write them in green, and -2, -3. Here's 6, 5, that's underneath the line. Here's -2, -3, it's on the line. Okay, on the line tells me that it must include the points that are on it. 6, 5 tells me points below the line must be included, which means our shading, if you wanted to do shading, is going to look like this, and it should be a solid line. So what is this thing? It's not going to be y equals, but y is less than or equal to. We're shading below it, so y is less than or equal to 2x plus 1. That's my final. Last question, number 45, same kind of premise. I'm curious. Well, actually, now that I see -7, -16, I can't use my graph for that. So we'll do the same thing as before using point slope form. -7, -16 is on the boundary line. So is 1, 8. So let's use the same slope bits. We have rise of this over run of this. 8 plus 16 is 24. 1 plus 7 is 8. 24 over 8 is 3. I'm going to substitute 1 and 8 for x1, y1. Y minus y1 equals m times x minus x1. And I'll add 8 to both sides to get y equals 3x plus 5. That's the original boundary line to draw a graph on. And then we'll figure out which points they're talking about, whether they work or not, and how we change this equals to possibly something else as we do some work on shading and all that. So up 3 over 1 and down 3 left 1 like so. Now they mentioned 1, 8. Oh, sorry, 1, 8 is on the line. Never mind. I thought they were saying it's a solution. So we're just going to go ahead and use this one like so. And boop. All right, do we change it to dashed? I don't know. It depends. They said, oh, these are not solutions. So let's use red. Let's make sure of it. -7, 0 is not a solution. 314 is not a solution. Here's the problem. I don't know where 314 is. It's a little above. -7, 0 is right there. I'm guessing 314 is on this line. Let's imagine it. If I kept going, what would be the case here? I'd go up 3 over 1 like this. That's at 211. And yeah, another up 3 over 1 would indeed be at 314. Now 314 is not supposed to be a solution to it. Neither is this. 314 not a solution means this has to be dashed. A point that's on a dashed line is not a solution. This is not a solution either. That means we do not shade on that side of the solution set. So as an overall, to me, that means the following. Shading below the line and a dashed line, which means y is not equal to. It is strictly less than. Given that we are in slope-intercept form on our thing, we can call that a less than, and 0, 0 should work out. And you can test it. But I'm going to change this thing here to y is less than 3x plus 5. Test 0, 0, you get 0 is less than 5, which is a true statement, and that works on that just fine. So that should be our final equation. Inequality there. All right, guys. That'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Now, keep in mind, this was not systems of linear inequalities. And you're like, why? How does this work in our chapter? The next section is systems of linear inequalities. And we had to start with this one going into it, so now we can make sense of what it means to shade and dotted lines and things like that. I'll keep on the mantra of shading above and below when we're in slope-intercept form, or testing 0, 0 when we're in standard form, or whenever I feel like that we should. So just get ready for some of those as we do 2 of them in 1. Always use a pencil for these to shade lightly. You'll thank me for it when we do our systems for sure. So thank you guys so much. Take care. I'm going to see you in the next one.